It's a metaphor for the human spirit, the condition. Something to represent our passion for innovation, for existence. One can even survive because the fire inside them might burn brighter than the fire around them. For that is the peak of human will, a representation of the fire itself. Or at least that's what some bandage guy said. Anyway, today, kids, we're learning how to start a house fire. But because we're not Neanderthals, we're going to do it with lightning. That's right, the lightning you get from your very own walls. So how do we access this wall lightning, you might ask? That's right, it's through a power outlet. It's stuff that you should have on most of your walls. Power outlets are usually right here at the bottom. Let's turn that into a black marker so we can actually see what I'm trying to write out. Oh, look at that, there's a little smiley face. Sometimes they're a little concerned face. They might look like this. Whoop. There's usually two of them. Those outlets may be the source of the voices you hear at night, or maybe they're just there for you to plug that sweet, sweet wall lightning straight into your iPads. Now let's get into some backstory about why we're trying to keep warm this winter. In the motherland, cold, cold Siberian winter, snow falls from the sky, a warning to those children who play outside. It is no longer time for snowball fight. No. When you get cold, you must take shelter within large building. Within your large building, the radiator is common in much Europe. We use gas, gasoline, propane. How do radiate? It's wonderful, thank you. What a steam. We didn't have central heating with hot air coming in whatever room you need. No, with radiator we heat water and hope that it does not break. Because radiator, it works by cycling hot water or steam through many pipe, through house, through building. But if pipe burst, you lose water, you lose heat, you lose life. See, in America, you have things easy. You have what's called central heating. This is when hot air is blown straight into a room, usually through heating coils that are in some AC outside. Or if you want a more localized version of heating, you get, that's right, today's experiment, the space heater. Space heaters keep you warm through a very simple design. They usually have a fan and some resistive wires. Fan blows, wires get hot. Look at that man sitting comfortably in front of a space heater in his own home, plugged into a safe wall outlet, with a safe, controlled, warm current of air blowing straight toward him. Now, unfortunately, some of us aren't that rich, so to make a space heater, there are a few key safety design features that must be followed. This list has been generated by Google's AI. You might be wondering, why am I not showing you real, actual, factual documentation for this same information? Google must have its sources, right? Well, of course it does. It's through the actual documentation. Unfortunately, that documentation would cost us several $100s to get a copy of. Thank you, dear government websites. So today's project will be built with no safety material in mind because, well, we don't have access to it. Now, to make a safe space heater, there are a few safety standards that usually should be upheld. For example, a certification label. Heaters have to carry this label from some testing facility to make sure that it's safe. Unfortunately, we neither have the time nor money to get that testing done, so we're going to skip right over that step. Automatic shutoff. If for some reason our space heater catches fire or overheats, there should be a temp sensor inside to turn it off. Unfortunately, temp sensors cost money. A tip-over switch. If for some reason the space heater were to fall over, we don't want it to directly apply heat to the carpet. Once again, that would cost money and time, so we're going to skip over that step too. Thermostat. This is optional, so you know what that means. Too expensive. Cool touch exterior. You see that word some? That means it's not required. A sturdy grounded cord. The recommendation is for something robust, something that could handle the electrical load. I argue that as long as it can handle that load for the amount of time you're running it, that's all that really matters. We're not running it for years on end, so 2 wires I found on my shelf should be good enough. Lastly, GFCI. We're not using this in a damp area, so we're going to ignore this too. Now, because we couldn't read true safety spec requirements, we're going to assume that starting a house fire is A-OK according to the government. Otherwise, that wouldn't be behind a paywall. Here's a picture of what that will look like. Boring exposition out of the way, I do want to say that I am an engineer. And if you know your stereotypes, that means I do a lot of meth for the ADHD. I also do a lot of math because that's what pays the bills. But what you'll find is neither of those statements are true.
I don't take anything for ADHD because I'm undiagnosed. I'm afraid of doctors because they're expensive.
And I don't do that much math because calculators exist.
To keep myself from over explaining the science into a blank screen,
I'm going to try to gloss over the boring parts of each process as I show you what doing it looks like in real life. First thing you're going to want to do is gather your materials. I forgot to take a video of this step because all you really need is metal and an outlet.
and to keep up with standard YouTuber fashion of overcomplicating parts of projects, the metal is going to be nails and wire.
Even though I said we don't care about safety, that only applied to the fires. So let's clear the suffocation hazard before it becomes one. Most nails you would buy are going to be galvanized. What that means is they have a nickel coating. That coating is there to keep the nails from rusting, but it'll also suffocate you if you apply too much heat. When you heat up the nickel enough, it reacts and forms nickel oxide. And you breathe it in, and your lungs will try to reject it because they're too bougie for nickels. So to punish the nails for their bargain bin drip, we're going to give them an acid bath. I'm using muriatic acid, which is a diluted hydrochloric you could buy at Home Depot. The reason this acid removes the nickel coating is because the chlorine in hydrochloric acid is attracted more to the nickel than it is to the hydrogen, so the HCl split and we get nickel chloride and hydrogen gas. While you're doing this, you're going to want to wear safety gloves and a respirator because the fumes are almost as toxic as HCl's relationship. All you need is a length of resistive wire and a bunch of nodes you can wrap the wire around. Those nodes can be anything you want them to be. I'm using nails. And naturally, you want to keep everything very steady, so you want a surface that you can drive those nails into, so when you tie the wire around them, they won't move much if you add tension. For example, a cardboard box. That's what I call recycling. You might notice that wire is taking a longer path to get to places than what would be shortest. That's because I'm trying to drag it out to meet a certain length requirement. Much like how my monologuing is there to pad time and extend the length of this video. Both attempts at elongation have a purpose. In the case of our circuit, that's because that wire has a certain resistivity to it. Resistivity is our measure to say how much a material doesn't want electricity going through it.
Resistive wire hits our sweet spot for resistivity, because we can cram current into it until it either reaches a point of stability or burns out, exactly as you'd expect of an American workplace. The specific material I'm using is called Kanthal because it's cheap and has a high heat tolerance. At this point, I can use the diameter and length of the wire to figure out its exact resistance. But because I'm sane and don't hate myself, I'm going to look at a spec sheet. Through trial and error, I found that a safe current the wire can handle before melting is about 6 amps. What you see on the right is 3 circuits. Mathematically, they're all the same, so we're going to use different diagrams for different parts of our calculation. Top right is the most simplified of the 3, showing total equivalent resistance and our voltage source. Voltage being 120, we can calculate a total power to be about 870 watts. On Amazon, these heaters usually cost about $30. Compared to our $5 of ingredients, we're saving about $25 in lieu of all the safety features. In the top left, we see a diagram showing more accurate depiction of what our 2 parallel tracks look like in terms of their total resistances. We use this to calculate how much current is going to flow through each half. Being the observant viewer that you are, you'll note that both those numbers are bigger than the 16.5 in the first diagram. I'll explain why that is when you get older. The even more observant among you would see that the math works out to only 5 instead of 6 amps, so we can make this baby burn even hotter. That's because I gave myself some margin for bad construction. And the diagram at the bottom shows a pretty detailed version of what I'm actually stringing up. Each resistor in the diagram represents one length of wire nail to nail. Now that I'm done blabbing about the boring parts, we're pretty much done with our assembly. Only thing left to do is add a few connections for positive and negative that we're going to plug into our outlet. And now we're ready to get to testing. Make sure you have your fire extinguisher handy, take it outside, plug it into the outlet, and see what happens. Now, as you might imagine, plugging metal into an outlet isn't hard to get right, especially after a few failed off-screen experiments and a home insurance claim. In all seriousness, this is a very dangerous thing to do, and you should not do this at home unless you know exactly what you're doing. So as any good scientist, I'm going to have my handy assistant touch it to demonstrate why you shouldn't. As Handy was kind enough to demonstrate, symptoms of touching red-hot metal include spontaneous combustion of the limb touching red-hot metal. Do not touch red-hot metal at home, no matter who recommends doing so. And it was constructed from UV resin, which has a much higher heat tolerance than your skin, but you'll see that it burns all the same when exposed to about 1000 degrees Celsius. So just dunk it in some water to ease the subject's pain. If you've been watching either of the other two screens so far, you'd note this is actually a pretty safe design, only flaw being self-immolation. We could fix that, but that would require a higher budget. I do have the budget, but I was too lazy to fix it a year ago when I started making this video, so I'm gonna leave it as is. If you've stuck around this long into the video, I want you to know that I appreciate your presence here. I realize I'm bad at this, but I do hope to improve over time. Anyway, next video is going to be a tutorial on how you can start local wildfires. I'm going to show you using my own lawn as an example. With that, cue outro.